All right. So we're going to look at some basic probability events, those type of things. We're going to get to towards the end of combinations and permutations. So bunch of probability stuff. All right. First thing, the probability. This is literally the most basic of probability you can get. When we're talking about probability, we're basically talking about the number of ways an event can occur divided by the total number of possible outcomes. All right. So we're going to see a bunch of examples tonight about playing cards and stuff like that. Like really simple. If I'm going to roll a die, a simple die has how many sides? 6. So what's the probability that I get a 1? 1 out of 6. What's the probability I'm going to get a 5? 1 out of 6. What's the probability that I get an even number? 3 out of 6. That's basic probability. All right. So that's in essence what this is telling you right here. It's how many ways the event can occur divided by the total number of outcomes you can have. Okay. And when we're talking about playing cards, talk about a deck of 52 cards, same concept. And we're going to look at some of those in a little bit. So. All right. So let's look at one that's a little different first. I'll do all of them just with playing cards and dice, which makes life a lot easier, but there is real life applications to this too, other than gambling. All right. So in this problem right here, they want the random sample of 2 officials. So that we want to pick 2 of the 5 jobs here, and then we'll ask some questions about them. So the first thing we want to do before we do that is we want to list all the possible ways. Because just like having a die or a deck of cards, you know the total number of outcomes. Yes? It was F was the number of ways the event can occur, and N was the total number of possible outcomes. So in this situation, or in most situations that don't involve like dice or cards, you have to come up with what are all the possible outcomes we can have. So if we're looking at picking 2 officials, we're just going to use the letters so I don't have to write out the whole names. We have governor and lieutenant, governor and secretary of state, governor and attorney general, governor and treasurer. Lieutenant governor and governor is the exact same as governor and lieutenant governor, right? There's no reason we need to have them both. So we're not going to use that one. So the next one will be lieutenant governor and secretary of state, and then attorney general, lieutenant and treasurer. Then we have secretary of state and attorney general, secretary of state and treasurer, and then we have attorney general and treasurer. Okay, does that make sense for all the options? So the easiest way when you're making a list, which it sounds like this is something everybody should get, but believe it or not, there's actually ways to do it. Just start with 1, go down, and then since the repeat doesn't work, you just cross that one off and literally do the exact same thing for those, and then just keep going. It's the fastest way to make a list that you don't forget things. If you randomly start picking them, odds are you're not going to get them all. Or you're going to repeat one, depending on how many numbers are out there, and you're not going to catch it. So I see that all the time when I have kids that I'm telling them, like, okay, look at a 2 dice. You're rolling 2 die. Give me all the outcomes. And they just start randomly writing down 2 numbers. And it's like, you're never going to get them that way. So be logical when you're coming up with your choices and how you're writing things down, so you don't miss any and you don't repeat it. So how many outcomes are there? 10. Okay, so that right there, that's my N. Remember, was F over N? That's my N. That's never going to change in this problem because those are all the outcomes. Okay? So what's the probability that we obtain the governor and treasurer? 1 out of 10. There's only one of those options, right? What's the probability that the attorney general is included in the sample? Right, because when we look at it, we have that one. We have 4 different ones that have the attorney general. So that would be 4 out of 10. Okay. And we could write that as a fraction. We could write that as a percent. If we divided it 4 out of 10 would be 40%. So depending on, at the end, depending on how you're going to use your answer and what type of person you're telling your answer to, depends on what information and how you'd want to present that information. All right. If you're talking to a normal person, you could say 4 out of 10, they probably would get that. All right. But if we're talking about like looking at like lottery systems and stuff like that, that it's a big number, telling them 1 or 2 out of 10,300,000,000 won't make sense to them. But if you say it's 1 out of 1,000,000, or you reduce it down to things like that, makes it a little more comprehensible to them. Or if you give it to them as a percent, normally most people will get the concept of a percent and make more sense to them. So when you're looking at giving information, your audience actually makes a big difference in how you would present that information. I don't care how you present the information to me. I can get it any way you want to write it down. As long as it answers the question, you're good. So 4 out of 10 would work. 2 out of 5 would work. 40% would work. 0.4 would work. All right. Let's look at some dice. All right. So in this problem, we have all the possible ways that you can roll 2 dice. It tells you that there's 36 possible outcomes. Now, when you're rolling 2 dice, unlike the last situation, 1 and 1 is different. It's 1 and 1, or 1 and 2, and 2 and 1 are 2 possible outcomes when you roll those dice, because they're 2 separate dice. Okay? So when you're looking at counting them up, you're going to count both options there. Okay? Because unlike before, where it was 2 people, that would make a difference. But in this situation, the order they come out could actually matter in terms of what you're doing. So we've got 36 possible outcomes. So 36 is my N or my F? That is my N. Okay, so we've got, so let's look at A. So I have over 36. It says the sum of the dice is 11. So we want to come up with all the possible combinations that come up to be 11. So when we look at it, 6 and 5 is 11. Is there any other way to get 11 on those 2 dice? No. So it's 2 out of 36. You could. That's what I was saying. Like, in terms of like when they're looking at it here, 2 out of 36 makes sense. All right, you can reduce it to 1 out of 18. That's fine too. So that's where knowing your audience and stuff like that. How would you want to present that to somebody else? So a normal person that knows dice and things like that, 2 out of 36 would make a lot more sense than 1 out of 18. Because they're like, no, there's 2 ways you can get 11, not 1. It's like it would. So, or you could just change it to a percentage too. So dividing 2 by 36 gives you whatever the percentage comes out to be. So me, I'll take either one. It's fine. All right. So B. Does my Does my N change? No. Still dealing with dice, so it's still over 36. This type we're looking at doubles are rolled. So which ones are going to become up doubles? So we've got 1, the 2 2s, the 2 3s, or yep. So we've got 6 of them. So it's 6 out of 36 or 1 out of every 6.
Each one has double.
Correct. Yep. There's 6 of them. Mm-hmm. So the basics of probability is that when we're looking at it. We're going to do a lot more complicated things with it, but that's the basis of any probability. Like you go to the casino, every game is based on this. Where they come up with how much you're going to get paid for each thing is based on this. So. How many different ways can I flip a coin? When I flip a coin, what can I get? Heads or tails? Okay. What's the probability that I get heads? 1 out of 2, right? There's only 2 possibilities. Heads is one of them. If I flipped it 10 times, how many heads am I going to get? Am I always going to get 5 out of 10?
No.
Could I get 10 out of 10? Yeah. I can get 9 out of 10. I can get 1 out of 10. I can get none out of 10. All those are possibilities, right? Now, that's where the difference between the expected probability and the realistic probability comes into play. So when we're looking at anything games of chance or any kind of things where you're actually going to do an experiment, you have your experimental probability, which is what happens when you actually do it. And then you have your theoretical probability, which is what should happen. So if I did 10, me getting 10 heads in a row, while unlikely, could happen. Would I get 100 heads in a row? Probably not, right? All right. There is a very slim outside chance, and I'd probably tell you to go play the Powerball if you had it happen, or I'd check the coin. But it's like, could it happen? Yes. Odds of it happening are very, very slim. What typically happens is the more and more you do, the closer and closer you're going to get to a 50-50 split. Okay? So when you start doing an experiment, if you do only a few experiments, you can get some weird results. But when you start doing a lot of those experiments over time, then you start to get to what should actually happen. And that's basically what this wonderful little slide here is going to show you. So come on, baby. There you go. So they did a couple times of simulations of flipping a coin 100 times. So you can see this one right here, they're flipping it. This one apparently liked tails. So tails came out a lot more. But as we got closer and closer to 100, it got closer and closer to that 50%. This one is another simulation of it. This one seemed to like heads a little more. But again, it started getting balanced out towards that 50% as we got to 100. And if we did it to 500 or 1,000, it would get even closer to that 50%. The other thing is, like, even if you get some variation, so if I got 55 out of 100 heads, that's 55% heads. If we're looking, but there was only 5 different, right? Like if the 5 of those heads became tails, I'd be exactly 50-50. If we're looking at 1,000 and I had 510 heads, now you're at 51%. 10 switched. So it's like it was more than switched over the 100, but the percent's clear because my bottom number is getting bigger. So you can start seeing, even though you might get that variation on it, the variation has to be a lot bigger to start getting those larger changes in your percent the more you go. So something to keep in mind when you're looking at it. In gambling, it's called the law of averages. It's like you play long enough, it's going to average out. However, if you play long enough and it averages out at a casino, it never averages out in your favor. The house always takes a cut. So no matter what you play long enough, the house wins. So when you get enough winnings, walk away. Because eventually the house is going to take it back. Yeah. It happens to a lot of people.
We won 106,000 4 years ago. And they took 42,000 in taxes.
Oh yeah. The government always takes their cut. What is it? The Powerball that they just won, the $1.3 billion Powerball. The tax bill is, I think, $400 million.
That's why.
Wait, how much did they win?
1.3 billion. So the tax bill was $400 million.
So I think I'd be okay.
Oh yeah, he's like, when you get that, it's like it's fine. But still, it's like when you're looking at, it's still a lot. I think after they took they took their lump sum, and actually it was 2 people. I think they ended up each getting, I think, like $325 million, something like that, at the end. Yeah, it was still, anybody would be happy with that. But you look at it, it's like when you start getting up to the large numbers, like they're really large bills. It's like 100,000. You still lost $40-something thousand in taxes. It's a big chunk. So,
where does the money go?
Yeah.
Right?
well, yeah, that's a whole nother conversation. All right. Let's look at a couple of properties of probability. So the first one is probability of an event is always between 0 and 1. Okay. So if we're thinking about it in terms of percentage, so this is just as a decimal. When you divide it, you get a decimal. If you think about it in terms of percent, it'd be from 0 to 100%. Right? Same thing as saying 0 to 1. The probability an event cannot occur is 0. That only occurs when the event can never actually happen. Okay, so the whole concept of when pigs fly, that perfectly makes sense. Pigs don't fly. It's impossible for a pig to fly unless you shoot it out of a cannon. It's not flying of its own volition, therefore technically it's still not flying. So that would be 0. Probability of an event will always occur. We'll go back to the government taking taxes. That's always going to occur. So that's a 1. Okay. So when you look at it, those are the two things that can happen. Okay. So a certain event's always 1, and an impossible event's always 0, and everything else is basically between, which is pretty much everything. 0 and 1 rarely ever actually occur, but everything's in there. It could be a very small chance that it's going to happen, but there's a chance. All right. There could be a small chance that it doesn't happen, but there's still a chance. So, all right, couple words or terms that you need to know. Sample space. That is the list of all possible outcomes for your experiment. So we're talking about flipping a coin, heads and tails. That's my sample space. Those are the only 2 possible outcomes. Rolling a die, 1, 2, 3, 4, 5, 6. Only possible outcomes. Unless you play D&D and have 20-sided dice, and you can go up to 20. So, becoming popular. Stranger Things brought it back, and everybody's like, oh, wow, what's that? I'm actually starting that club at my school. So, that's your sample space, is the list of possible outcomes. The event is a collection of outcomes. So, what happened? So, this is typically a subset of the sample space. It could also repeat. So if I'm flipping a coin 10 times, the event is the outcomes of each of those flips. So 7 heads, 3 tails. All right, my sample space is still heads and tails. That would be my event, the 7 heads and the 3 tails. All right, before we flip over to the next one, does anybody in here not know what a deck of cards looks like? Good. All right. How many suits are in a deck of cards? Suits. There's 4 suits in a deck of cards. How many cards? How many of each suit? 13. It's quick. 52 divided by 4. All right. So how many face cards are in a suit? Does Ace have a face on it? Well, it is. It's 1. So actually, as crazy as that, I asked that question because we had a large debate on that because I'm writing a book, and there was some probability stuff in there, and it asked for face cards, and the answer that was in the book was different than the answer I got. And I'm trying to figure out why. It comes out to find out that that was the distinct difference. They were counting Ace as a face card, where all the information I was finding says Ace is not technically a face card because there's no face on it. Although, like most people think, well, it's Jack, King, Queen, Ace. It's like those 4 cards. But so it's one of those things you have to clarify. So what I went through and what we added in there was face card, parentheses, Jack, Queen, King. So you had that actually listed in there. So this way there was not a discussion about it. They actually were able to calculate the probability of it. But those are things sometimes you have to think about when you're looking at probability. All right, so we've got our deck of cards. So there's our deck of cards. They list the Ace first, which is where you get the 1. So, all right. So let's find my questions, because I know there's a couple of questions that I needed to ask because I didn't put them on there. Not the questions. There we go. All right. So if I said, what's the event that is, so if I'm saying just the King of Hearts, is that my event or is that my sample space? Sample space is the deck of cards. So if I pull out just the King of Hearts, that's an event. Okay. So my sample space is still the entire deck. Now, what's the probability that I pull out a King of Hearts? 1 out of 52. All right, so there will be one of those cards in my event. So if I'm going to pull out, make sure I have everything that can possibly come out for that event, there's one King of Hearts. What about if I selected just a king? There's how many different, if I selected all the kings? There's 4, right? So my event is the 4 kings. So what's the probability that that would occur? I pull a king. Hmm?
Well, if there's only 4, would it be 4?
Yep, 4 out of 52. I select all the hearts. What's the probability that I select all the hearts? 13 out of 52 or 1 out of 4, because there's 4 suits. And this is why I asked the question. What happens if I picked all the face cards? It's 12 out of 52. Because there's 3 of each suit.
Joker's not a part of it, right?
No, the Joker is not part of a standard deck of playing cards. So don't have to worry about the Joker. That's the outlier. Depends on what kind of game you're playing with. I don't think there's any actual games at the casino that use the Joker. I don't think so. I could be wrong.
Are there any games of all these Joker?
When I played Tekken, we played Switch, and they
Oh,
played
okay.
that Joker game.
Yeah, there's a few, like I know people who play poker with the Jokers and stuff like that because it's just an automatic wild card. So it's like it just depends on how they're playing. Like, but they're like friendly games. They're not. Yeah, it's like those type of things. So, but yeah, I don't think they play with the Jokers at all. All right. So, a little bit more terminology now that we can use. So the first thing is when we're talking about an event, you're typically going to give it a letter. All right, so your events are going to be labeled with letters. So we're going to say the probability of A, and A is an event that we've listed as that event. So there's few things when we're looking at them in terms of letters that you're going to see quite often when we're talking about probability. First one is not. Okay, not whatever the event is means the event didn't occur. So, for example, if I say not, well, my event is the hearts, hearts. So I pull all the hearts. That's my event. If I said not that event, what would my event be? What is the opposite of me pulling all the hearts? Right, but what would be the actual event? What would I actually have in my hand if I did not pull the hearts? I would have what? What's the other 3 suits?
Yeah.
I'd have all the diamonds, I'd have all the spades, and I'd have all the clubs. Okay? So not is the exact opposite of what it is. So if I said not heads, it would be tails. All right? If I said not even, it would be odds. So if I took the not events and the actual event and I added them together, what would I get? Right, but what would be the probability of that? If I took my event and I took my not event and I put them together. Correct. That'd be everything. Okay. So sometimes, depending on what you're looking at, it's easier to find the not event than it is to find the event. Okay. It's easier to find those things that don't necessarily work and then just subtract that from the whole to find my answer. Okay. So if I said, I want everything except for the kings. Well, I know there's 4 kings. So my not event would be the 4 kings. So if I said 1 minus those 4 kings, I'd get my answer. That's easier to think about sometimes than thinking about, okay, how many other options are there? So there is a place for the not. Both A and B occur. So you'll see this written a couple different ways. You can see the little and symbol there, or it actually will be written as and. So that means both events would occur. Okay. You also can see in some situations this. You also can see that. That's the union of A and B. I don't know if they show it in this book. Honestly, I haven't gone through the entire book long enough to figure out if they actually show it in this book or not. But you will see that in some other math classes and other situations. So I just want you to make sure you understand that those two mean the same concept. It's both the A and B. The other option you have is A or B. Okay. Actually, I messed that up. That's actually this way. It's the intersection of A and B. And I'll show you why in a second. This one's the union. I'll show you why right now. So, or means either one of them would be correct. So these actually come from, actually, no, I'll give you a chance to finish writing this because I'm going to switch the slide in a second. Yeah, I didn't put it there. All right, so these come from A, B. Anybody know what this is? Starts with a V. It's a Venn diagram. So if we were looking for, the first one was A and B. That is the intersection. That's A and B. That's where they both occur. Okay. If we're looking for A or B, that's everything inside both circles. Okay. If we were looking for the not, this, that would be the, that actually would be listed as not A or B, because it's outside of everything. If I said not A, I'd have also had to include the B circle in that with the red. So since I didn't include either one, that's not A or B. You can actually see that also written as nor A or B when they take the not and the or and put it together. Anybody in engineering, electrical engineering and stuff like that?
Not that I started anything yet.
You're gonna see these come up when you do logic gates.
Yeah, I'm familiar with
Yeah, and gates, NAND gates, OR gates, NOR gates, all those are the logic gates. Same, very, very similar concepts to this. So, all right. Very good. Okay. So the first thing we're going to look at when we start talking about events, since we're starting to get into more a variety of different types of events. Oh, that's okay. I will put that one back. So we're going to do those together. That was a different side there. We have things called mutually exclusive events. So the Venn diagram I just showed you there are A and B mutually exclusive. What do you think it means by mutually exclusive? Huh? Right. They would. So basically, there's no overlap. So is A and B mutually exclusive? No, not in this example. That's actually a very important thing, because when we start looking at how we can put probabilities together, if they're mutually exclusive, I can do it one way. If there's overlap, if I just add the two together, for example, I would get that overlap. So I have to subtract out the overlap because I'd be counting it twice. So we need to remember, we need to know if the two events are mutually exclusive or if they're not mutually exclusive. Okay, so those are important things to remember when we start to look at events. Let's go. Where was I? Where was I? Nope. All right. Really? All right. So here's our events. So what event happens when I pull a B and C? Huh? Actually, yeah, being event A in this case. So I would pull a what? I'd pull the King of Hearts, right? So B and C mean both have to occur. So since B says it's a king and C says it's a heart, both of them have to occur. So that would only be the King of Hearts. What would happen if I pulled B or C? Yes. Right. So I'd have all the hearts, in addition to all four kings, well, the extra three kings, right? Are those two events mutually exclusive? No. All right. Because that's fine. It happens. It's so because B and C has that one king that overlaps, they are not mutually exclusive. Okay. What about C and D? What would I get if I did C and D?
Would be
Are events C and D mutually exclusive?
would have a heart face card.
So that would not be mutually exclusive. So mutually exclusive means there's no interaction between the two. So if I said, actually, give me an example of two things that you could pull out of a deck of cards that would not be mutually exclusive.
7, it's like B could be an event is pulling out a 7.
Okay.
C is event is pulling out a face card.
That works.
They can't.
Correct. There's no overlap between them, right? The 7's not a face card. I was going to say a face card and an odd card, same concept. So yeah. So that would be mutually exclusive. Those two events cannot occur, have nothing in connection to them. All right. Where C and D, I could have face cards that are hearts. So there is some overlap there. Okay. All right. Actually, it's 4-8. Are C and D out of this list mutually exclusive? What's the overlap? Yeah, the Jack, Queen, King of Hearts, right? What about C and E? Very good. What about D and E?
That's true.
That's mutually exclusive based on our previous conversation. All right. What about D, E, and F? Okay. So we can have more than 2 events that are mutually exclusive, right? We can have, yes.
What's up with the floating and the-
I don't know. I literally copy and pasted it from the book. And I'm actually physically looking at the book and it has the and there too. My guess is whoever wrote this, now that I know the other end of publishing, is that somebody, when they wrote it, they were thinking about adding something else to it and then decided against it and forgot to erase the and.
I think the and is like and B.
No, because it would have been, yeah. They have commas after. So you might be, that was somebody who was purely a grammar person and didn't know anything about math, which also could happen. Yeah, it could be that, but either way, it shouldn't be there. Yeah, that's why I'm spending a ton of my time going through and editing other people's work that's going into a book, and it's like all the little mistakes that people make. It's like, now I understand why there's so many little mistakes in books, because it's just every time somebody looks at it, we catch another one. Like, we looked at this book like 5 or 6 times, and the 6th time we looked at it, we caught another mistake. Yeah. So it's like, it never ends. That's why the only problem I have with this, because then they do a revision, and they make you buy the new revision when it's basically the same book. I don't agree with that. Huh? Yeah, it's basically, yeah, you're paying for their mistakes. All right, D, E, F, and G. Are they mutually exclusive? Why? I think that's the only overlap. Is that Jack?
So if you give us like, if he's like on a test, you give us D, E, F, and G, exclusive. There's only one instance where it isn't.
That would not be mutually exclusive. Say it's not mutually exclusive because of the Jack. That would be the answer for that question. So if they only gave you, like, if they said D, E, and F, G, are those groups mutually exclusive? Then we could look at it a little differently. But since they said D, E, F, and G is that all 4 of them mutually exclusive? If there's any overlap, they're not mutually exclusive. And that Jack makes it not mutually exclusive. All right. This is why mutually exclusive is so important. It's because of right here where we're looking at a special edition rule. If we were looking at what's the probability of pulling, actually, we'll go back to a dice because it's simpler. What's the probability of getting a 3 or a 5 on a die? Okay. So my event 3 is 1 out of 6. My event 5 is 1 out of 6, right? The probability of either of those occurring, so or those, is 2 out of 6. All right? Because the 3 event and the 5 event are mutually exclusive events, right? If I said, what's the probability of me getting an odd number or 5? So odd would be 3 out of 6, right? 5 would be 1 out of 6. So if I just added those, I get 4 out of 6. Correct. Because they're not mutually exclusive, this addition rule doesn't work. So that's why it's so important to know if the events you're looking at are mutually exclusive or not. Because if they're not mutually exclusive, if they are mutually exclusive, I just have to add the probabilities together and I'm done. If they're not mutually exclusive, I have to take away that piece that overlaps because I would count it twice. Like in that situation, I'm counting the 5 twice. Okay. So that's where that piece comes in. It doesn't matter how many I have. So like A, B, C, D, E, F, whatever. It doesn't make any difference the number of events. If they are all mutually exclusive, I can add those back together. Okay. All right. I don't think you guys can read that. That's tiny. See if I can make that a little bigger. Is that better? All right. I can't make it much bigger than that, unfortunately. Now I need the problems. There you go. If you have the book, it's on page 174. So if you want to look at the actual list of them. If you're using the online book, it's on page 320. All right. Are all these events mutually exclusive? How can we say it? They're all mutually exclusive. Okay. So, what else does this look like? Now we're going to get to go back. The relative frequency table. All right, so we can turn this into a histogram, whatever we want, right? And when we were designing those, one of the things we made sure we were doing when we were setting up your classes is that there's no overlap in the classes. So this one ends at 49, this one starts at 50. Okay. And there's nothing, in the way this one's set up, there's nothing in between the 49 and the 50. So they were all even breakpoints. So it wasn't a 49 and a half, for example. All right, so we've determined that they're mutually exclusive. So now technically I can ask you any questions I want, any events, and we can add them all together, right? So what is the probability that somebody is going to, what is this actually? Is this acreage? Size of farms, yeah. So what's the probability that I'm going to find a farm with over 1,000 acres? .078. Okay. Because you're going to add events F and G. Okay. So the probability of event F or G is 0.078. What's the probability that I'd find a farm under 50 acres? Nope. 387. 387. Yes, you did. You started adding and then I think started subtracting. So yeah, 0.385. You're going to add events A and B. Okay. Doesn't matter how I state my question. So in that question, the second question I asked, I said under 50 acres, right? And the first one, I said over 1,000 acres. Doesn't matter how I asked my question. If I said over 1,000 acres, does 1,000 acres count? No. Now, I totally didn't do that on purpose, but I just caught that in my head while I was going through it because the next thing I have to talk about is literally inclusive versus exclusive. So when you're talking about counting things and adding things up, you have to also think, because a lot of times you're going to be doing this stuff, it's not going to be just simple numbers on a page. It's going to be problems that you're going to have to figure out. So when you're looking at certain things, you want it, when they say over 1,000, that technically means 1,001, not 1,000. You could either say, you could say it's including 1,000, or you can say 1,000 greater than or equal to 1,000. Yeah, 1,000 or higher. Like those terms mean things and how you actually list them. So it's like if you said 1,000 greater than 1,000 or more than 1,000, this table I don't know what the 1,000 was, so I can't technically remove that. So at that point, you're just gonna have to go with it and say, yep, we're good. But depending on the data that you have, you might be able to make those determinations. So, and that could change things. So be very careful when they're looking at, especially when you're reading things, how the wording is. Okay. A lot of times you'll see, like, for example, say add all the numbers from 0 to 1,000 inclusively. That means that it's including 0 and the 1,000. Okay. Things like that. So this way, you know, those numbers actually do count and not just the ones in between. Because if it says between 0 and 1,000, it actually means between 1 and 999. Not the 0 and 1,000, because those are not between 0 and 1,000. So remember I said statistics is one of those subjects, the things in math that you can lie with. And being able to parse people's words and meaning is very, very important when you're looking at this, because a little switch of the words means something, could mean something completely different. And depending on how you hear it, depends on what you're going to think. So just keep those things in mind.
So like cup half full, cup half empty.
Yeah, it's basically the same thing, but those have very different meanings to people. So, all right. I actually mentioned this one already. This is the complementary or complementation rule. Basically, it's the opposite of not. So when we were looking at the problem, remember I said it, sometimes it's easier to find the event and then do the opposite of it to get what I want than it is to find the actual event they're asking. So in this case, they're saying less than 2,000 acres. So if we go back and look at this, less than 2,000 acres, I'd have to add this one, this one, this one, this one, this one, this one. Okay? But this has to add up to 1 because this is all of them, right? So if I, instead of adding them all up, if I just say, well, that's the one I don't want, just subtract that. So if I did 1 minus the 0.036, I get 964. So 0.964. That's my probability. So sometimes it's better to go the opposite direction than it is to add up all the events. If I said under 50, we already figured out that, right? So if I wanted the opposite of that, if I wanted greater than 50, I could just take that away from 1, and I now have my other answer. Okay. So that's kind of what that is. Sometimes it's easier to go the opposite direction. But the only reason to do that is because this rule exists. That's the one thing that sometimes drives people nuts about math. We have a lot of rules and stuff, but those rules allow things to happen. And sometimes, like in science class, you do experiments and things like that, and it's like, okay, I've done it enough. It makes sense. It works. However, then 10 years later, we figure out, well, maybe that just doesn't work anymore. And we have to change things. Or the next month, as we saw in the past couple of years. We got more data. What we thought was true is no longer true. Okay, that happens in science. It never happens in math. In math, once you have a rule or something that goes down, it has been proven to actually work always. It'll never change. The one nice thing about math. So no matter how you do it, if you see a rule and a math teacher tells you a rule, that rule will always work. So we have stupid things like this that just completely make sense. Like, yes, that makes sense. But we have a rule written down to say it. So that because now people will use this rule to do other things. And it's built on rules that we know work. Like they proved that the triangle is 180 degrees in it. That was something that had to be proven before we could do everything else with triangles at some point. We learned it as, that just totally makes sense now. Or a circle is 360. It totally makes sense. It's just there. But somebody had to actually prove originally that actually was true. There's my wonderful Venn diagram. So we talked about the addition rule when it was mutually exclusive. If it is not mutually exclusive, we still have to have some kind of rule. It is, so we have the probability of A plus the probability of B minus the probability of A and B. Because if I added up all of A and all of B, that stuff in there I'm counting twice. I've hit one of them away. So if they're not mutually exclusive, I need to know what the probability that they both occur. And then I have to subtract that out. So we did the odds and the 5, and those up, I get 4 6. The overlap was 1 6. So it's 5. So I subtract that out. That one actually, the entire B was inside of the A. So that's the general addition rule. This will always work if they're mutually exclusive. That's just 0 because there is no overlap. So the rule here still will work. Okay, it just goes back to that the simpler rule. Right. So this is that's why this is general, and the other one was a more simplified version of it. So if you only want to remember one, just remember this because it always works. Just sometimes that last thing is 0. All right. What's the probability that a selected card is either a spade or a face card? So when we look at this one, we're not going to do it the 2 different ways because I'm not going to make you actually just sit there and write them all out. So event A is a spade. Event B is a face card. So what's the probability of A? What's the probability of me getting a spade? 13 out of 52. Now, this one I would keep out of 52 because we're going to do some other stuff to it. I know it's always going to be out of 52. Any problem I give you with cards is going to be out of 52. So if we keep all the fractions out of 52 and we can deal with reducing it afterwards, it's going to make your life a lot easier. What's the probability of face card? 12 out of 52. Mutually exclusive? No. Okay, so there's overlap. So what's the probability of A and B? So what's the probability that's a face card that's a spade? 3 out of 52. Okay. So we have to add those first 2 and then subtract off the final piece. And then that'll give me the probability of A or B. So we got 13 plus 12 is 25, minus 3 is 22 out of 52. Does that make sense? You think about the number of cards, right? We have the 13 spades plus the 3 face cards that are hearts, plus the 3 face cards that are clubs, plus the 3 face cards that are diamonds. So that would be 22. Okay. That would have been how we did it without the general rule addition rule. We'd actually figured out like exactly how many cards there was. Right? I do have one more. All right. 2 more of these. All right. Characteristics of the people arrested. So records for 1 year show that 73.9% of people arrested were male, 12% were under the age of 18, and 8.5% were males under the age of 18. If a person was arrested that year is selected at random, what is the probability that the person is either male or under 18? So, what's the first event? What is the 73.9% though? They're male. So my first event is males. Now, the probability of that is the 73.9%. Okay. What's the second event? Under 18. Now, what's the probability of that event occurring? 12%. Okay. Are those two mutually exclusive? Those two events? Could you have a male under 18? Then they're not mutually exclusive. Okay. So, since they're not mutually exclusive, we need to know what the overlap is. My pages are totally off on yours. There you go. I really need an actual copy of the book. Normally, the online books are actually like pretty similar, like close, but Pearson did it like totally weird. So it's like, and they don't have like, if they had the page numbers on the bottom, it wouldn't be a problem, but they don't. So we need the overlap. So we have probability of A and B. And they also give us that percent, which is kind of nice of them. It's 8.5%. Kind of like they actually do what they were talking about at this point, right? All right. So we have our probability of each event, and we have the probability of the overlap. So we know if they were male and under the age of 18. All right. So now the question they had was, they have the or. So it's A or B. So how do we figure out A or B? Yeah.
You just add 73.9, 12, and then subtract 28.
Yep.
Then you get, I think 88.4. I didn't just calculate.
Don't go there, we won't trust you.
Actually, it doesn't make sense, 88.4. If we add them together, we get 85.9. If we're subtracting 8.5, it's got to be under 7. It's got to be under 80.
I did the math wrong.
It's fine.
But I think I was like the idea.
Yes, you have the idea correct, just not the number right. 77.4. That sounds right. I'll tell you, 99% of the time, I am not doing the numbers in my head. But I know about what the number is going to be. Like, I knew this one was under 80. So as soon as you said that it was over 80, I knew it was wrong. And actually, that's a really good strategy to use in anything you're doing, is estimate, get a general idea of where the answer is, because it's really easy to type something wrong in the calculator. Like, my guess is you typed 0.8 instead of 8. Or you did 0.8 because you even said 0.8, which would have given you about the answer that you came up with. So it's the little things that could happen, but if you generally know where the answer should be, you can catch a lot of those mistakes. All right, so here's a interesting question that's not on the board. What does what does event A or B represent? In realistic terms, what does that represent?
Male and under 18.
So male or under 18. So it's males, all males, right? And one under 18 added in. Almost. What's the only piece that wasn't included in the very first statement of males? Okay. What's the In terms of this problem, I can clarify this because the world has changed. In terms of this, what is the only other sex they could be talking about? Female. So they're talking about all males and females under the age of 18. Because the males under the age of 18 are already included in the males. Okay. So if you look at this based on the numbers here, how many females under the age of 18 were arrested? You can figure that one.
1.5.
3.5.
No.
3.5. You're right. 3.5% were females under the age of 18.
But over the age.
That you don't have enough information to get.
Why not?
Well, I guess technically you could figure out how many females were arrested by just doing the opposite of males.
Yeah.
So you could figure that part out. So yeah, I guess you could figure out females in general, females over the age of 18. Yes. And then if we subtracted out the 3.5%, you can figure out how many females over the age of 18 that were arrested. So yeah, you could do the not males and get the female aspect of it there. This is actually one of the problems that we're going to have with a change in how we're doing demographics, is that up to this point, you were able to compare data going backwards really easily because it was all standardized. It was the same thing year after year. Now, when we're starting to add in a lot more demographic information and a variety in there, you might not be able to easily go back and look at how it compares, which makes numbers muddy, which makes numbers be able to up it up to a lot more interpretation of what's going on. So it's like we have to be careful on how we're looking at some of those things and how they're being reported, because you could change people's opinions on how things are going with that. Like there was a change. They're trying to change, like right now, if you're a juvenile, you're under the age of 18. However, I believe you can still be tried in an adult court under the up from 16 and up, depending on which crimes and stuff you've committed. They want to change that so it's only under the age of 18. It doesn't matter. 18 under, no matter what you do, you're still charged in the juvenile courts. But that's going to start changing, because then they're going to say, well, now at that point, more juveniles will be charged in the juvenile court than in the adult court. So that the number of juvenile court cases are going to go up. So people might say, well, there's going to be there's a lot more juvenile crime now. Not necessarily. We've added more people in there. So, or more violent juvenile crime. Well, no, because we never even had those cases in that situation before. So it's like, that's where you can start to see people using information to skew public opinion one way or the other. So, like, interesting little things to keep in mind with how we're looking at it. All right, so here's what we're going to do. Before I switch over to the next thing, I'll give you guys your break. About 15 minutes? 7:20? Sound good? And then we'll come back and we'll do the other part. What's up? Okay. I'm sorry. What's the probability of event F? One out of. So the probability of F is 1 out of 6. What's the probability of out? Was it? 3 out of 6. Okay. What's the probability that a 5 is rolled given that the dice came up odd? Okay. So what's the probability? You're right. What's the probability that a 5 is rolled if you know the dice came up odd? It's 1 out of 3, right? Okay. So that's known as conditional probability. So it's the probability of F given O. All right. So basically, and this one's going to be 1 out of 3. So if you know the dice came up odd, that's the condition. What are the odds that it came up to be a 5? There's only 3 possible outcomes at that point. So what conditional probability is doing is, remember the whole thing at the beginning of probability, it was the number of events you wanted out of the total number of events, right? Conditional probability is changing the total number of events. It's giving you a condition to look at and go, okay, this is now your new sample space. What's the odds it's coming out of that? Okay. So if I said, what's the what are the odds that I pick a blue jacket if I'm only looking at the females? Okay. I think it's 1 or 2. Well, she's got a blue shirt on, so we'll do 2. Okay. So out of however many females are in the room. So it's like that's, if we're just saying what's the odds of you getting a blue jacket, I'd be looking at the whole room and my sample space there. So conditional probability is changing that condition on the bottom. All right. What's the conditional probability that a die comes up odd given that 5 is not rolled? So what's the probability that a dice comes up odd if we know 5 wasn't rolled? It'd be 2 out of, nope, not 6.
2 out of.
Be 2 out of 5. I know the 5 wasn't rolled, right? So now there's only 5 possible outcomes that could have come up. So it's 2 out of 5. So conditional probability is one of those ones that's kind of tricky. All right. And I will admit it could get a little fuzzy when you're looking at it because in most probability, you don't change the bottom. And the conditional probability is changing that bottom number as well. All right. So when you're looking at it, it's like, okay, what is my condition? And now what's the odds of it happening out? If this happens, that's my new sample space. Now what's the odds of it happening? Yeah.
It's changing any bit specifics.
Yes, basically. So like, what is the odds of me picking a face card if I know I picked hearts? Three out of 13. Because I picked hearts, so now there's only the 13 hearts, and there's 3 face cards. So it's 3 out of 13. Okay. And it can come in handy too, because like if you're looking at it like, this is why I don't gamble at casinos very much anymore. Because I can count cards. So, and counting cards is all conditional probability is. So when you're looking at playing blackjack, we'll just take a single deck of blackjack. It's like, you know the cards that have come out. So those now are no longer part of the sample space. So that is a condition. Now, what's left over, what's the odds of you getting blackjack? Or what's the odds of actually, typically when you're counting cards, you're not looking at what you're getting, you're looking at what the dealer's getting. So what's the odds of the dealer is going to get blackjack or 21? And then you bet accordingly. But that's where that condition comes in. Now, because your bottom number is changing, your odds are increasing or decreasing depending on what came out. Okay. So that's where that conditional probability comes into play. And it comes up all the time. It's one of those, and it's one of the most confusing parts of probability because you're not used to that bottom number changing. So, huh? Yes. So it's not illegal. It is not against the law. They, however, casinos are private property and they can set their own rules. So don't go to the casino and count cards. I will tell you actually.
I don't know.
So, all right.
Have you seen the movie Casino?
Yeah, and
That happened.
there's a few of them. 21 is the biggest one that about the MIT group. So nope, it's actually true. So actually, right now, most casinos have their tables are set up that it actually the computer is counting the cards. So everything is digitalized now. They have the cameras and everything else. So the computer is actually keeping count of the tables. When you're counting cards, you don't win more or lose more. You win or lose the exact same number of same number of hands. When you're counting cards, you bet differently. So when it's in your favor, you bet higher. When it's not in your favor, you bet lower. Therefore, you're making more money. That's how they catch you because the computer knows when it's in your favor and they're watching your bet stats. So they're watching how you're betting. And if you change your bets, depending on the count of the cards, at some point, depending on how much money you're making, somebody will walk over to you and say, hey, we're going to take you over here to do something else and then walk you out the door and tell you never to come back.
Okay,
They're not going to come break your legs or anything else like that, but they're just going to tell you never to come back. So
You
you
get to cash out first.
depend. In all honesty, it depends on how much money you made.
that's a great question.
It depends on how much money you made. So, but yeah, they're not gonna break your legs. They don't like it. They consider it cheating. And
They cheat all the time.
oh yeah, they cheat all the time.
That's
But
okay for them to do it.
absolutely.
Yeah, right?
So, but that's their business. That's which you know when you walk in the door. So yeah, I don't play blackjack at the casinos. I play roulette all the time, but I don't play blackjack. It's actually blackjack's the only one you can do it to because of the way it's done.
With roulette, can you like yourself?
So no, actually, so here's the difference. And actually, going back to what we've been talking about, it's actually a very important difference. And one of the things we're going to do at the end is actually a roulette problem. So what's the difference between roulette? Everybody know what roulette is? It's a wheel with the ball. What's the difference between roulette and blackjack? And what we've already talked about so far in class. Correct. Roulette is mutually exclusive. Every event is separate. The one event does not impact the second event. Okay? You can get, every time you spin that wheel, every number has an equal probability of coming up. Okay? Right. It does. It's that right. There's everything. However, in blackjack and poker, the cards come out, odds change. So they're not mutually exclusive events. Okay? So that's the distinct difference in those situations. So same thing with slot machines. Everything is mutually exclusive. Every event is separate. One event doesn't have any impact on another event. So you can hit a jackpot and literally the next spin hit a jackpot again. That's possible. Except that the video slot machines now are actually programmed to go off at certain times. They've actually always been that way. In Vegas, they used to program the slot machines to go off so that you always heard clinking of coins. So you'd want to go to gamble. This was way back. You'd want to go gamble in the Vegas casino when it was less busy. Because again, if you walk into a casino and it's dead silence, you're not going to gamble there, you're going to walk out. If you walk into a casino and you hear the coins clinking and the ching, ching, chinging, people are winning. You're more likely to bet there and play. So they wanted to always have that sound going off somewhere in the casino. So you had a better chance of winning if there wasn't a lot of people playing. So, and now the video machines are all programmed to go off at certain times. So yes, it's totally rigged. The table games are less rigged than the slot machines. All right, so that's where conditional probability really comes in. It's like when you're thinking about those kind of concepts and stuff like that. Now, let's look at another example of conditional probability. So conditional probability, we just basically talked about it, is it's a probability of B given A. So it's the probability that B is going to happen given what's already happened in that condition. So in essence, A becomes my new base number. All right, so let's look at this. Where's my problem? Where's my questions? All right, so this is a contingency table. If we get outside of the realm of card games and gambling, this stuff actually does exist as well. These are known as contingency tables. Basically, if we look at it, we've got the breakdown of, so under 30 number of full professors, associate professors, and so on, and then the total. Based on these numbers here, we can come up with, what page was it?
187.
187.
Oh, that's a different.
Oh.
187.
There's one that has the numbers, and there's one that has all the percentages. They'll both work for what we're going to talk about. Actually, if you don't want to do the calculations, the percentage one's probably going to make your life easier. When you're looking at a table like this, we have multiple things that we can look at. So if I just wanted to find out the number of full professors, if I'm going to randomly select a full professor, what's the probability that I'm going to get a full professor? What numbers would we divide? How many full professors are actually? Yeah, how many full professors are there?
430.
430. And how many total? Right. So the probability of R1, which is what they consider a full professor, is 430 over 1164. And you just divide that and get the percent. Okay? That's just the probability of that. Now, that's not a conditional probability. Okay, because there was no condition put on. It was just we were picking that one event. What's the odds of me picking somebody who's 30 to 39, given that they are a full professor? Right. So now, if I pick A2 given R1, that's 52 over 430. Because now my full professor is now my base number. And I want to know what the odds of me picking a 30 to 39 person is. Person in their 30s. Okay? That's why if you look at the other table, they've got the percent numbers there. So you'd actually have the actual percent number there. What's the odds of a person 50 or over being just an instructor? Four out of 33. So now this one actually, I wasn't just looking at one event, right? I was looking at two, because 50 and over was 50, this one, and that actually. It was that one and that one I was looking at. Just happened to be the other one was 0. So it was A4 or A5 given R4 is 4 over 33. Okay. Does that make sense? All right. That's actually, yes. Conditional probability or the table? Oh, it's in this condition. So given, it's normally say A2 given R1 is normally how you read it. Yeah. Conditional probability? Yeah.
What's it say in front of the A5 on the bottom?
Okay.
Oh, it's A4 or A5.
Oh,
Because I was looking at these two rows. So it was either one of those. It just happened to be that one was 0. And when I was picking random ones, I didn't even look at the numbers when I was choosing them. Otherwise, I would have chosen something that wasn't a 0. So that's where these come in. Now, if you look at the other, what page was the other table? 188? Oh, 180 was the one that had the, okay. Which one had the percentages?
182.
They put it a whole bunch of times in the book. Yeah, the online one, we keep saying, go back to this page.
182 has the percentage.
Okay, yeah, one of them has like the percentages in there, and you wouldn't have to do the division, they're already done. So you can see these tables written multiple different ways so that you wouldn't necessarily have to go through and do it. Now, those percentages are all based on the total. So the 2 out of it's 2 divided by 1164 is the number that goes there. So, but then you can sit there and figure out, okay, what's that out of? So we would do the same thing. It'd be this out of whatever the percent was there to do the calculations. So if you're going to do conditional, it would be the same concept. You just use the percentages to do the division at that point. All right. Yep, did that. All right, so this is the conditional probability rule. So depending on what information you're given, depends on how you do these calculations. So it's the probability of A and B. So it's the probability of them both happening divided by the probability of N. So let's see if I can find that other table real quick. So I don't think I put it here. Oh, actually, I'll use that one. So that's what I was just saying a second ago, actually, when we were looking at that table with all the percentages there. It's a percentage of both happening. So it's in that box divided by the percentage of that total column or row, depending on the way we're looking at. So you still would divide those percentages or probabilities at that point. The other way this is going to actually help us is we're going to look at another rule in a minute. Because this is a formula, all three of these have numbers that would probabilities that go with it. We can manipulate like this times this is going to give me that. So you could actually do some calculations with it to figure out other pieces, depending on what you're given in a specific situation. All the math comes into play now. All right, let's look at this one. All right, so this is the table of marital status and gender. So now these are all in the probabilities. This is the probability distribution of it. So what's the probability that adult selected is divorced, given that the adult is male? So it's divorced male, right? So that's that one. And we were given that the adult is divorced. So we're dividing it by the 0.104. So the probability that it's male, given that it's divorced, is 0.044 divided by 0.104. Or did I read that backwards? Oh, I did it backwards. This is the other problem that comes up with conditional probability. All right, let me read that to you again. Determine that the probability that the adult selected is divorced, given that the adult selected is male. So what is the sample space? What is the group we're looking at to start? We're given that the adult selected is male. So that comes first.
44, 4.
Right. Exactly.
If we have a question on just on the stats, do we have to write it differently than these stats going?
Yeah, I would actually divide it at that point. If you're giving it in decimals, don't leave it as just divide it to give you the actual decimal, which is what I'm going to do in a second. So when you're reading the thing, you have to make sure that the piece that you're given is the second part of it. So in this case, we're selecting an adult that's divorced, given that they're male. So it's divorced, given that they're male. So it's the 0.044 divided by the 0.485, which equals 0.091. So that's what I'd expect to have seen at the end.
Well, yeah, it was divided.
Yeah, you're just dividing. You're just dividing. Normally, one or whatever else, you just write the number to be done. But since they're not, like this is not going back to your audience. That doesn't really mean anything to anybody. Like if you said that, it's not going to have context. That would. If we're looking at that point, it's 9%. That would have some meaning for context. Okay. So when you're setting it up, the key piece is what are you given is the base number. What do you want is the top. Okay, that makes sense? And you can see how easily it is to revert to it because I did. All right, let's look at another one of those. Yeah, that's the other one. Let's do what's the probability that the selected person is female given that they're widowed? So we're given that they're widowed, right? So that's M3. And we want female. So that's the 0.050 over the 0.063. And what does that equal? This one you have to do it carefully. There's no way you're doing this one in your head. So 0.794. And whenever you're doing your rounding, always round to the number of places they gave you. So since all of them are in 3 decimal places, give you 3 decimal places. Yep.
So the first example that you listed, you used the number on the side, the 0.485. So how come you didn't use the 0.515 instead of the 0.063?
It depends on the direction you're asking it. So in the first one, it was the number of males given they were divorced. Or no, sorry, it was the number of divorced given they were male. So we were given all the males and we wanted the probability that they were divorced. So that's why the males goes down the bottom, because that was what we were given to start with. And this one, I said, what is the probability of me picking a female given that they are widowed? Okay. This just goes to show you women outlive men. So, and it's starting. It's like, all right. So that's where, depending on direction, really matters in this case. All right. Because when you're looking at it, remember back to the very first thing it was what we wanted over the total. Same concept here, except the total we're given is a subset of the whole. So in this case, my total was widowed. And the last one, my total was male. And then I looked at a piece of those. Okay. Good questions. All right. So this was the general multiplication rule. That's what I was talking about a second ago. We're looking at the conversion of them. So this is no different than the other rule. I was just the conditional rule, where it was P A and B divided by P and A equals the condition. So this is just a manipulation of it. It's just like algebra. We can move things around and multiply and divide and stuff like that. Let's see which example did I use next. Yeah. I didn't use all the examples. I wanted to make sure I picked the right ones. And a lot of these times you really have to look at what you're going to be given. So when you're looking at probability, you have to look at what you're given and what you're being asked to find. Okay. So sometimes you're going to be given certain types of information. You have to understand, okay, are they giving me a conditional probability? Are they giving me just an event? Those type of things to decide what we're going to do with it. This helps us find an and event, the actual, like the intersection of two events, if I'm given a conditional probability and something else. So depending on what they give you, depends on what rules you're going to have to use. And that's really, I think, the hardest part of this, and the hardest thing that you're going to have when you're looking at probability is being able to take the word problem and say, okay, this is what they're giving me. How do I get to what I need to find? Okay. And that's where you're going to have to start looking at that. That's the problem solving piece. And that's the part where I think you're going to have the most things when you're looking through the examples and stuff this week and the exercises, is looking at that. I would almost, when you're going through and doing them, I'd almost ignore what section it is. I just open to chapter 4, open to one of the exercises and start looking at the problems and ignoring that section. Like, don't say, oh, I know I'm in the section, so I'm going to use these rules. It's like, go to a section, try a problem, say, okay, how do I find this? And then if you can't figure it out, then start, okay, what section am I in? Like, then go back to, like, okay, what do I need to be able to find these things? Like, and start looking for common terms in the actual word problems. And see, and those are the things that are going to start to help you figure out, it's like, okay, well, I need to use this when I'm given that. Or I need to use this when I'm given that. And that's going to help you be able to solve those things later on. So, because in the essence, you're never going to be given, it's like, okay, use the the multiplication rule to solve this problem in the real world. You're going to be, here's a problem, find me the answer. So it's like, you need to start figuring out how to use your tools to find those answers. Okay? And unfortunately, teachers do a great job of teaching you all the tools, and not always a great job of telling you how to use those tools, because we just don't have time to do it all. It's like, there's so many little pieces and stuff that we have to get through. I will do next week, before we cover chapter 5, I'll set aside probably about a half hour at the beginning of class. If you have questions on the exercises, bring them in. And we'll go over some of the questions that you guys have. But also, if you have questions before that point, email me and I can go over them. And I might just use those as the first ones I go over in class. So, but yeah, as you're going through them, if you're getting stuck on things, ask. And maybe even do the exercise at the end of chapter 4. So this way they are completely mixed up. Like, look at those to see, figuring out which one it is. And I think all the odd ones are in the back of the book. So do the odd ones so you have the answer. So you can just say, well, was I right or not? Because I don't have the solution guide to this one. So. All right, Congress. Let's look at Congress. What Congress are we in? I'm trying to figure out how old this book is. Anybody know? Every Congress gets a number. We're in. Really? Doesn't tell me. All right. So this is the 113th Congress, which I'm not sure what year this was in. So this is the composition of Congress. So the 113th Congress, 18.7 of the members are senators, and 53% of the senators are Democrats. So what probability that a randomly selected member of the 113th Congress is a Democratic senator? Huh? Oh, in the 117th. Okay, so this is 8 years ago. Because every 2 years. Or actually, it might be every year. So it might be 4 years ago. All right. So what did they give me? In this one. All right. So, okay, let's take a. So you gave me the percentage center. So let's take a step back. What are the two events they gave me? There's two separate events they gave me.
Member selected as Democrat.
Okay. All right. So they gave me the Democrats and they gave me the senators. I always want to add an E on the end of Democrat. You can tell I'm a math person and not an English person. I can't spell to save my life. All right. So it's Democrats and senators. So those are the ones that, those are the two events. All right. And we want to know the probability that it is a Democratic and a senator. So a D and S. That's what we want. Okay. All right. So now, what did they give us? So we know that the probability of the senators, is 18.7%, right? Now, 53% of the senators are Democrats. So is that the number of Democrats? No. So what was my base piece? My base piece was my subsample space is senators, right? And then I chose Democrats out of the senators. So it's Democrats that way. And that's 53%.
$53 of 18.7. Be the percentage.
Yeah. So now if we go back and look at the formula, we have that was 18.7. So I'm actually going to change this to 0.187. And then this was the Democrat, given that they were a senator, was 0.53. So if we multiply those, we will get D and S, which is what we were looking for. Okay, which was what? Somebody got that number for me? Not the Burger King. We have a calculator up. 0.187 times 53. So we got 0.099 for 9.9%. And that would be picking just a random person out of all of Congress. Okay, is 9.9% that they would be a Democratic senator that I would choose. So that's where, like I said, you have to really look at it as like, what are they giving you? And you have to figure out what the events and stuff they gave you, because depending on how you write your events depends on how you're going to set this stuff up. They kind of helped you with your event here, because we want those two things. So those two things have to be my event for that, because we want both those things to happen. Now, how do they give me the other information if we put aside? Stupid thought. Let's see if they actually did it right. Yep, they did. Okay, good. How many members of Congress are there? Does anybody know? All failed your civics classes, I see. Huh? There's 100 senators. How many in the House? No. A lot more than that, actually. 435.
Fair enough.
It's about half, that number comes up because you need that actually to pass normal legislation. Yeah, it's 435. That's where in presidential elections that number 535 comes from, because that's the number of electoral votes. It's one for each senator, one for each person in the House. That's how they come up with those numbers. So that's why I just did real quick. I'm like, okay, did they do the 18.7% right? Because I did 100 divided by 535 to make sure that that was the number of senators or less. Another stupid question. I went to Washington in 2019, actually went to the House and everything else. Do you know why the Democrats are called left wing and the Republicans are called right wing? It is exactly where they sit. It is exactly where they sit in the Senate. The Republicans are on the right side of the Senate, and the Democrats are on the left side of the Senate.
It's not like a worldwide term, though. Like,
No,
it isn't.
no.
Not every country is run by a bipartisan system.
Yeah, it's now most countries, if they do have a bipartisan system, they typically will use our terminology. But and like England and stuff like that, you don't hear left wing, right? You hear Labor and what's the other one?
You're hearing
Yeah.
it more now.
Yes, because it's becoming. You gotta remember, a lot of culture comes from the United States and spreads. So, but yeah, it's not. It literally came from the right side of the Senate and the left side of the Senate. As stupid as that sounds, and that actually came from Parliament in England, where they sat on opposite sides of Parliament.
Oh.
If you ever want to see something hilarious, find a channel or a YouTube stream of actual British Parliament. They're sitting there on opposite sides screaming at each other sometimes, like full out screaming at each other. It's hilarious.
In Brazil, they actually fight.
Yeah, they've had them in England, like literally, yeah. Yeah, it's
Normal right now.
it's crazy. But yeah, that's where left and right wing came from. I was like, once you saw it, it's like, okay, it makes sense. And then I'm like, what happens if somebody wasn't one of those sides? It's like you'd have three sides. That wouldn't make sense in a circular room, but maybe one of these days we'll see that. I'm not holding my breath though. All right. No, the independents sit with the independents get to choose who they're caucusing with. Because right now there's actually two in the Senate. Bernie Sanders is technically an independent, and there's an independent from Maine. They both caucus with the Democrats, though. So right now, for all intents and purposes, the Republicans and the Democrats, neither one of them have a majority in the Senate. But because the two independents caucus with the Democrats, and the vice president's a Democrat, that gives the Democrats the majority in the Senate. So right now, the Democrats have 48 and the Republicans have 50 in Senate. But that's how they split it up. That whoever, if you're not one of them, you have to basically choose one. So where government works. Welcome to civics. All right, let's get back to probability now. The thing that all those politicians exploit to a tremendous ability. All right. So Professor Weiss's introductory statistics class, number of males and females is shown. The first, where was I? That's where it was. Hold on. I got to find the problem now. There we go. Thank you. All right. So two students are selected at random from the class. The first student is selected is not returned to the class for possible reselection. That is, it is sampling without replacement. That matters. Find the probability that the first student selected is female and the second is male.
First female would be 23 out of 40.
All right. So the first is female is what? Would you say 23?
3 out of
Yeah. So the first, so we have, it's the probability of just being female, because this one's just out the thing. So probability of just being female
then it would be 17 out of 3.
is 23 out of 40. Exactly.
Because the kid doesn't come back.
Right. So now I have a conditional probability. All right. Even though it's a very basic prediction or a very basic conditional probability, because I'm just basically removing one, it is still technically a conditional probability. So because I'm not replacing, it's this written as the probability of male 2 given female 1 is 17 out of 39, because now I've already taken one of those females away, so I only have 39 left in the class. So the probability of getting the female first, so female 1 and male 2, we'd multiply those two. Now, you could do this as actual fractions or as decimals. It's up to you. It doesn't make much difference. You're still going to get the right answer. But this is one of those ones I would not write as a fraction at the end, because again, very little meaning to it at that point. The percentages is a much more useful piece of information.
How do you multiply?
Fractions?
Wait, so the bottom one is saying that's the probability of you picking
A female and then a male.
Okay, so how do you find that with the top?
You're just going to literally multiply these things. Because remember, this is that multiplication rule we just looked at. So when you're looking at, and we're going to get into this a little bit more multiplication in a second. Basically, once you have multiple probabilities, you can just multiply them together, and that'll give you the probability of those events happening in form. So the probability of picking a female first is 23 out of 40, and then the probability of picking a male second, given that female is already gone, is 17 out of 39. So you multiply those two fractions together, and you get 0.254. So about 25%. And that makes sense, given the proportions of the class. It's about a 1 in 4 shot of being able to have that happen. Remember we were talking about mutually exclusive? When we're talking about conditional probability, you can have something known as independence. If the probability of B given A is the exact same thing as the probability of A to be, or probability of B to begin with, they're independent of each other. That means making that selection has no impact on the next choice. So that would be the difference between like replacing and not replacing. If we didn't replace, it wouldn't matter. Probability would come out to be the same. So if the probability given in this is the same as the probability of the whole, then they're independent of each other. Very similar to mutually exclusive. It just means there's not a connection between those two events. Let's skip that problem. And go to this one. Yeah. Oh, I didn't skip that one. Okay. I'm going to skip that one. All right. So, if the two events are independent, so just like we were talking about with the addition rule, we're mutually exclusive. If the two events are independent of each other, which means one event does not have any impact on the other one, I can just multiply them to get the probability of the two events happening. So the difference here is when we're looking at addition, it was or. So it was A or B happening. And that's where they need to be mutually exclusive. Now we're looking at A and B. So now we're looking at both events happening. Okay, so that's when we're multiplying. So if you're looking for two events and either one can happen, that's the or, it's the addition. If you're looking for two events to both happen, that's the multiplication. Okay? So going back to that concept of what are they asking, what do you need to use? So or is addition and is multiplication. Make sense? Let me write that so people can make sure you write that. So or is addition and okay. So in this situation, we're going to start looking at the and events. And the only difference between if they're independent or if they're not is what you're going to multiply. So if they're not independent, you have to use the conditional probability to figure out the second and third one. Like we did with the females, we took one of them away. We took one away from the base. So that's going to change that number. If they're independent, I don't have to worry about changing them. They're separate pieces of each other. So I could just literally just straight multiply them. All right. Told you. Now we're going to go to roulette. Because remember, that was the thing I was talking about where your card games, they're not independent. When you take a card out, it changes the base probabilities. So that's where that conditional comes in. Roulette, every time you spin that wheel, it is an independent event. So they have the nice board up there, and you see like black, 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 red, black, black. And it's like, oh, it's going to have to come up red. It's a 50. Well, actually, it's not even a 50-50 shot because there's two green ones on there. Basically 50. So you have that piece there. Every independent roll is a separate situation. However, just like we were talking with heads and tails, the odds of heads continually coming out, it gets less and less as you go on. And that's basically what we're looking at here. So actually, we'll do that one first real quick. So the first time I flip a coin, the probability of getting heads is what? 50%, right? Okay. What is the probability of getting heads twice in a row? Are those two independent events? Yes. So based on the multiplication rule we were just looking at, the first event is 1/2, right? And the second event's 1/2. So what's the probability of getting two heads in a row? Nope. 25%. Because it's 1/2 times 1/2. Okay? Does that make sense? So first time, it's 50-50. It's 1/2. Second time, if I want two in a row, it's 1/2 times 1/2. If I wanted three in a row, It'd be 1/2 times 1/2 times 1/2. So now we're at 1/8. There's a chance of me getting 3 in a row, which is about 12.5%. If I went again, we're now down to about 6%, 6.25%. You go again. Anybody remember the penny trick in high school? It said, do you want a penny or $1 million today or a penny doubling every day? You'd always want to take the penny doubling every day because at the end of 30 days, you'd have like, I think it's like $3 million or something like that. Same concept here. We're doubling the bottom's doubling. So to get 30 heads in a row is minuscule. So like when we're looking at roulette, same concept happens. If you start seeing black coming up multiple times in a row, the probability is getting really low that it's going to happen again. It absolutely can happen again because there's no rule against it, but the probability is getting lower and lower. So you start to play the odds. All right, so in 3 plays at the roulette wheel, what's the probability that the ball will land on green the first time, black the second and third times? So, first thing we have to figure out is, are those events independent? Yes, because what we just talked about, 3 rolls in the wheel are all independent. So, we have A, we have B, and we have C. So the first one was green. How many green numbers are there on a roulette wheel? There's 2. And how many total are there on a roulette wheel? 38. So there's 2 green, there's 18 red, and there's 18 black. And all your payouts are based on 36, not 38. The 2 greens are basically the house hedge. So you've got 2 out of 38. Now for your black, so black is on the second and third ones. How many black numbers were there? 18. So it's 18 out of 38. And then 18 out of 38. So we'd multiply those 3 together. We have 2 over 38 times 18 over 38 times 18 over 38. So the probability of it happening is 0.012%. So 0. Yeah, it's Desmos. And if you click that little button right there, it'll give it to you as a fraction. And it'll always give it to you as a reduced fraction. So yeah, this is Desmos. This is the same thing we were looking at. I did mention it in this class, I think. But yeah, it's just Desmos.com. They have this in the graphing calculator, which is kind of nice. We're going to use this actually a little bit too, because we're going to talk about permutations and combinations, which the buttons are right there. So great little scientific calculator. So, and the great thing about it is the way it shows, you type the things in, it looks like exactly as you type it in, so you don't have to try to remember like parentheses and all that other stuff. So we got 0.011 or 12%. So that is, so now if I change that to a percent, so we can think about it in terms of percent, it's 1.2% chance. Okay. So it's getting pretty low. But it's not 0. Yeah, typically if you land on a number, so say you play, I like, my birthday is August 22nd, so I always play 22. So if you land on 22, you get 35 times your bet. Okay? But there's 38 numbers on the wheel. So that's how they make their money. So because if they pay you exactly the odds, they won't make any money. So that's the house's cut, basically. So if you played that number and every number came out, you played it 38 times and every single number on the wheel came out, you'd only made 35 times your money. So you'd have lost 3 times your bet. So it was funny. This girl was very similar. It was like she was playing, basically, she's putting the quarters all the way up the roulette wheel, up the thing. So every single time this wheel spun, she won. But it was always a little less than she bet. But she won every single time. So she thought she was doing great. But every time she was losing, like it ended up being like losing like one chip every time. The dealer's like, she's been here for like 4 hours playing. and just like because she kept winning. So she thought she was doing great. But she was just a little bit every single time. And roulette, you don't play with your chips aren't money chips. They're colored chips. So you change your money in and then they convert it back. So it's like it's harder to figure out how much money you actually physically have in front of you because of the way the chips work. So all the little things. Oh yeah, that's what she cashed. She goes, "What?" I was like, she probably was like, "I was winning every time." It's like, yeah, that's what happens. So all the little things that happen at a casino. All right, let's look at this. This goes along with what we were just talking about. So, state license plate. This is actually the way it used to be in Connecticut. It is now 2 letters and 4 numbers. Is it 4 numbers or 5 numbers? 4 numbers? No, it's 5. It's got to be 5 numbers because otherwise it's the same as we had before. Yeah. Because I know they went up to 7 digits. So our license, so it used to always be 3 letters and 3 numbers. Those were our license. How many different license plates are there? So now we're actually, in this case, we're not looking at a probability, right? We just want to know how many there is. But that can turn into a probability because now we're basically finding our sample space. We're finding out how many numbers are on the bottom, how many total license plates there would be. Now we can figure out probability based on that if we wanted to. So whenever you're looking at a problem like this, I like using boxes. So let's look at we have 6 boxes, right? Okay. The first one's a letter. How many letters are there? No, how many? The first box is a letter. How many letters can go in that first box? 26. So there's 26 letters, right? How many letters can go in the second box? 26. How many letters can go in the third box? 26. How many numbers can go in the fourth box? It's 10. 0 is a number. So you got 0 through 9, which is 10 numbers. So we have 10 numbers here. We have 10 numbers there. Okay. So to figure out how many possible license plates there are, we just multiply all those numbers. So just that would give me 17,576,000 license plates. We didn't have 17 million cars in the state of Connecticut. However, a lot of times once they issue a plate, they don't reissue it. So over the course of time, those numbers are used up and they don't reissue them because the license plate was still attached to the car of that person and the information was there. So that's why they don't reissue the plates. So we probably did have like 15, 16 million cars at some point over time in the state of Connecticut. It's crazy when you start thinking about it.
Specific classifications.
Yeah.
Commercial combination.
Yeah. All those crazy things, motorcycles, and all of them have to be licensed and have a plate on them. So then you got the custom plates and stuff like that in there too. All right. What would change if we couldn't repeat something? So what would change if they were not independent? How many letters would be in the first box? 26. How many letters would be in the second box? 25, because I could not repeat the letter that was in the first box. Does it matter which letter was in the first box? No, I just know that there is one letter in that first box. So I can't use that letter again. Whatever letter happened to be, it doesn't matter. I just can't use it again. So there's 25 more letters in the second box. What about the third box? Now it's 24, because I've already used 2 of the letters. And now the numbers. 10, 9, and then 8. So now if we multiply that, now I have to do 10 times 9 times 8. Now we're down to 11,232,000. So we have with replacement and without replacement. Now, in either of those situations, does order matter? Is ABC different than BCA? And the way we did it here, those are 2 different things. So order doesn't matter. Okay. Or let me rephrase it. So order matters. So like those are 2 distinct values. ABC and BAC are 2 distinct combinations of letters. Okay. So that's going to come into play when we're looking at the next thing. And the last thing we're going to look at today. I'm going to skip factorials just because we're not actually going to do them. So we're going to look at 2. We're going to look at permutations and combinations. I am not, so this goes back to the same thing I was talking about with this standard deviation. I am never going to make you do this formula here. Okay? There's buttons on your calculator. Actually, on every scientific calculator, you don't even have to use the one online. That has NPR and NCR. NPR is permutations and CR is combinations. Okay? And the difference between the 2 is order matters or order does not matter. Okay? So in the situation we just talked about, ABC and BAC were 2 distinct values. So order matters, that's a permutation. Okay? If ABC and BAC didn't matter, those were the exact same thing, it'd be a combination. Okay? So if order matters, it's a permutation. If order does not matter, it's a combination. And we're going to look at them both. That's literally the only difference between the 2. Thank you. So, anybody ever go to the horse track? Problem is we don't have them in Connecticut. So like here, if ask somebody in New York, yeah, people go to the horse track all the time. Exacta. So an exacta is a wager at the horse track where you pick the top 2 horses. So the question is, does order matter? Does it matter if the horse you pick comes in first or second? Yes. So order matters. So if I pick Secretariat and American Dream as 1, 2, and American Dream comes in first and Secretariat comes in second, I lost. Okay, even though the same 2 horses were first and second, the order matters. So it's a permutation. So when you're looking at NPR, when you're writing this, because how you write it actually is going to end up mattering. NPR. It's the number, so the number you have, so in this case it's 12, and you're choosing 2. Okay. So we have 12 of them. And we're choosing 2. So if you go to Desmos, that's exactly how you type it in. So there's 12 horses, I'm picking 2. That means there's 132 different ways that I could pick those 2 horses out of the 12 that were originally there. Nobody's at the horse racing, so I can't ask the other question because I know there's one that order doesn't matter, but I can't think of the name of it off the top of my head.
What's a,
This? Desmos. DESMOS. I thought there was a word on this thing, but apparently, oh, there it is. I'm like, I was going to say, I knew it was there somewhere. There you go. They have 2, they have a scientific calculator and they have the graphic calculator. So this is the scientific calculator. And if you have they have 2 different apps. You can download the scientific app to your phone, or they have the graphing app. So you can download either one of them or both of them to your phone. Or if you go to the website, it's going to work exactly like the app. The only nice thing about having the app is you don't need the internet to use it. And depending on which classroom you are in this building, that can make a big difference. This one's got pretty good internet. My other night does not. All right, so pick the last one. Combinations. So the only difference between the 2, one order matters, one does not. Who is old enough to remember Columbia House? Columbia House. We used to get things like buy a tape for a penny and get 10 tapes, or they went to CDs. And, yeah. I saw the problem, like, I have to use this problem now. It's like who drove Columbia House out of business because they never bought the other CDs that they were supposed to buy for $20 a piece. All right, so Recruit 2 members, the Compact Disc Club advertises a special introductory offer. You buy 1 CD and you get 4 of them free out of a choice of 69 CDs. So the question, when you're looking at this to determine which one it is, does the order you pick the CDs matter? Because that's going to depend on which one you use. So you bought 1, that's out of the thing. You're picking 4 from out of the 69. Doesn't matter the order you pick those 4. No, if you pick Metallica, then Motley Crue, then Will Smith, and Bon Jovi, it doesn't matter if you pick Bon Jovi before Metallica, you're still getting those first CDs, right? So the order does not matter. So again, this situation we're looking before, ABC and DAC are the exact same thing. So we're using combinations. It's done the exact same way when you type it in Desmos, except we're going to use, in this case, NCR, and we had 69, and we're choosing 4 of them. So it's always how many you have at the beginning. Whenever you're plugging in, it's always how many you have and how many you're choosing. So in this case, we had 69 different CDs. We're choosing 4 of them. So we had 864,501 different ways to choose it. Six, 4, 5, 0.